What do you see when light passes through a crystal? It might be a diamond, or perhaps ice, or something you pick up off the beach and hold up to the sun. That interplay between light and crystal structure is beautiful. Well, at the atomic scale too, this interplay matters. The relationship between crystal planes and electromagnetic radiation is a fundamentally important aspect of my work in material science. Let's look more closely. This is a shield. Crystal structures are deduced by the diffraction of known radiation incident on solid material. The three-dimensional regularity of the unit cell in crystalline material results in coherent scattering of the radiation that has wavelength lambda, and energy of the scattered radiation is the same as the incident radiation. The directions of the scattered beams are a function of the wavelength of the radiation and the specific interatomic spacing of the planes from which the radiation scatters. The intensity of the scattered beams depends on the position of each atom in the unit cell and on the orientation of the crystal relative to the direction of the incident X-ray or radiation. Those beams that scatter in a constructive manner result in the allowed reflection. The intensity is a non-zero value. Those beams that scatter in a destructive manner result in unallowed reflection. The intensity has a minimal value. Each of the constructively scattered beams depends directly on the wavelength of the incident radiation. Historical records show evidence of von Laue's diffraction experiments before the publication of William Lawrence Bragg's explanation of diffraction of radiation by crystalline solids. However, it was the inquisitive William Lawrence Bragg's attempt to resolve an intellectual debate between his father, Bragg, and Loewe, his advisor, that resulted in the formulation of the famous Bragg's law. Bragg, the father, described the diffraction as billiard ball scattering or kinetic scattering. Loewe argued that only optical rules determine the occurrence of diffraction, that is, wave interactions only. Radiation acts as waves, and the scattering depends on optical laws of scattering. For example, the law of reflectivity. And constructive interference, that is, the waves in phase add constructively, and waves out of phase add destructively. These published rules even gained a name, the Loewe equation. Loewe's description of diffraction in three-dimensional space required solving 3 equations with 12 unknowns. That's tough. And Bragg's rebuttal stated that any symmetrical element present in the diffraction pattern reduced the number of unknowns. It also stated that only particle-particle interactions induce diffraction. The kinetic theory required that the particles scatter from atoms coherently. That's meaning the wave doesn't change at all, and the particle does not lose any energy during the scattering event. Even the earliest Loewe experiments supported this account. Bragg utilized all of the above precepts to derive a simplistic description of coherent scattering, where n lambda equals 2 subscript DHKL sine theta, where lambda is the wavelength of the radiation, DHKL is the spacing between the plane from which it's scattering, and theta is the actual scattering angle. Bragg derived this simple description of coherent scattering from an array of periodic scattering sites, such as atoms in the crystalline solid. The scalar description of diffraction considers the case of monochromatic radiation impinging on a sheet of atoms spaced at specific distance, DHKL, where HKL is the Miller indices of that specific plane. The wavelength, lambda, of the radiation is smaller than the interatomic spacing, DHKL. Typically, in crystalline solids, we desire to measure atomic spacing on the order of the lattice constant. That is on the order about 0 to 2 to 0.4 nanometers. Hence, we must use radiation with a wavelength that's less than 0.2 nanometers. The range of the wavelength includes those of X-rays and high-energy electrons. Based on this description of diffraction, we can conduct experiments to determine the distance between reflecting planes, crystallographic structure, coefficient of thermal expansion, texture, which is preferred orientation, stress, and the composition of thin films. So, take the time to notice what happens to light. Watch it dance as it bounces from a crystal chandelier or from a diamond ring. Look at the icicles in the low winter sun. But also take the time to think about what is happening inside at the atomic scale. Remind yourself of the interplay of wavelength and crystal lattice. Bragg's law is very important. This was ASU. Thanks for watching.